So in this session, I covered the uh, causes of voltage drop in alternator, and so that voltage drop is due to armature resistance. This is a R effective, nothing but effective resistance. So if you take a synchronous generator, so it's definitely stator winding, stator winding having some resistance. So that resistance is called as a effective resistance, and due to this resistance, some of the drop will be takes place, and this is very less when compared to the remaining drops. And here another one is armature leakage reactance. So armature leakage reactance is nothing but L. L is for leakage, X is nothing but reactance. So XL is nothing but armature leakage reactance. So basically, what is leakage reactance? What is leakage reactance? So, for example, if you take this is the north pole and this is south pole, and the flux links flux always from north to south pole. And for example, this is a conductor is available here. So look at this one carefully. This conductor linking only this one and this one, nothing but only these two flux are linking this conductor. Such a flux are called useful flux. So whatever the flux which is linking with the conductor, such a flux is called useful flux. And the flux doesn't link with the conductor, such a flux is called leakage flux. Leakage flux. Leakage flux. So some of the armature flux may not link with the stator conductors, and also it will not nothing but it will not links with the stator conductor. Such a due to that, some of the reactants will be wasted. Such a reactance is called as a leakage reactance. That is called leakage reactance. And last one is armature reaction. So this armature reaction, this is also available in DC machines and also in synchronous machines. In DC machine, only one effect is one. There are two effects will be there. One is a cross magnetization effect, and next one is demagnetization effect. Demag Cross magnetization effect and a demagnetization effect in DC machines. So for that, we have different formulas. ATD per pole, I think, but demagnetizing ampere turn per pole, and ATC per pole, nothing but cross magnetizing ampere turns, like that. But if you take this alternate synchronous machines or alternator, whatever it may be, so this DC machines nothing but only resistive in nature, no effect of inductor and capacitor, nothing but because of non-availability of inductor and capacitor, only this is a cross magnetization effect will takes place. Cross magnetization effect only it will takes place and this effect of inductors and capacitors will be neglected in case of DC machines. But unlike a DC machines, if you take a synchronous generator, synchronous machines, for example, synchronous machines, and sorry, so these synchronous machines will affected by the resistive loads, inductive loads, and capacitive loads. So that because of this one, there are different types of effect will be takes place on the armature. Basically, armature reaction is nothing but the effect of Effect of main field flux on armature flux. That is nothing but a armature reaction. This effect depends on resistive load, inductive load, or capacitive load, or combination of RL, or combination of RC, or combination of RLC, all. And because of this resistive load, cross magnetation effect, cross magnetation will be expressed because of the inductive load, demagnetization effect because of the capacitive load, magnetization effect will be takes place. For example, if RL load, R for cross magnetization, L for demagnetization, both will be takes place. Cross magnetization and demagnetization effect, both effect will be takes place. And so finally, I want to give a conclusion that armature reaction is common in case of a DC machine, but in case of synchronous machines, but in case of DC machines, only we need to take into cross magnetization and demagnetization. Cross magnetization, demagnetization effect will be takes place. But in case of synchronous generator, along with these two, another effect, uh, cross magnetization, demagnetization, magnetization effect. Magnetization effect extra will be takes place in this synchronous machines, and I will explain in details in further about that. So next, I want to give a small definitions. So what is the synchronous impedance and what is synchronous reactance? So for that we need to know what is synchronous speed. Synchronous speed is the speed. This is the relationship 120 f by p. The synchronous speed is the speed at which it will rotate at a constant frequency and constant poles, and the machine which is rotating at constant frequency and constant poles such a speed is called a synchronous speed. At that speed, whatever the armature resistance and whatever the total reactance and sum of vector sum of these two is called as a synchronous impedance. So first of all, before learning this synchronous impedance, let us see the synchronous reactance. Synchronous reactance. So earlier I discussed leakage reactance, leakage reactance, and armature armature reaction reactance. And some of these two is called as a synchronous reactance. X is for reactance and S is for synchronous. And ZS is nothing but synchronous impedance. XS is nothing but X is nothing but reactance. Z is nothing but impedance. Suffix I am placing S, so that's why this is synchronous reactance. X here, S is nothing but synchronous impedance. Synchronous impedance is nothing but the vector sum of armature effective resistance plus synchronous reactance is called as a synchronous impedance. So these are the basic definitions which are useful for the problem solving purpose. And the next one is armature uh, leakage reactance. Generally, uh, the major components slot reactance and end winding reactance and tooth tip reactance. These are all reactance is called as a leakage reactance. And generally the definition is slot leakage, end winding leakage reactance, and tooth tip leakage. So these are all called leakage reactants. Leakage reactance is nothing but I already told you the flux which does not link with the conductor. Such a flux is called leakage reactance or leakage reactance. So that leakage reactance is maybe in any manner, slot leakage or end winding leakage. End winding leakage reactance are tooth tip. So if you take this one, this is armature slots, and here tooth tip. These are called tooth tips and tooth tip leakage reactance. So that we cannot say that leakage reactance will belongs to a particular location or particular uh, space, particular place. So that these are all different types of there are different types of leakage flux will takes place. And now we already discussed this is synchronous reactance. Next one is a vector diagram of synchronous generator or loaded alternator at a unity power factor. So, so I will draw the model one. First of all, vector diagram is nothing but so E is equal to induced EMF E naught is equal to end voltage, nothing but load terminal voltage V. These are the vector sum plus IARA plus J IA XL, nothing but leakage reactance plus ZIA AXA armature leakage armature reaction resistance. And here in all IA is common, so that I'm writing here V bar plus I'm writing with different pen IA RA plus J here IA is common, JJ everything is common, J IA I'm taking common here IA XA plus XS. So the voltage induced EMF V naught can be represented in terms of load voltage and ARA plus Z. This is imaginary term armature resistance and sorry XL leakage reactance and armature resistance. So we need to draw the vector diagram. We need to draw the vector diagram based on this one. This one. For the leading load, this is the UPF load, unity power factor. Sorry, unity power factor load. So that's why first of all, E naught is equal to V. V like this. We need to draw V like this, and then this is V and IARA drop. Next one is IARA drop. We need to draw the IARA drop. So this is V into VIA. Both are in phase. In phase because UPF load V and IA. So that IARA drop also in the same direction of IA. This is IARA drop, which is similar to the transformer phasor diagram. Next one is IA XL. This is IA XL because of 90 degrees phase shift between resistance and reactance. IA XA XL, sorry, XL. This is next one is IA XS. IA XS. So that if you want to draw the IA XS, so IA XA, sorry, this is IA XA. This is nothing but IA XS. This is IA XS. XS is nothing but sum of the leakage reactance plus armature reactance. So if we add all, we will get this is induced EMF. So this is a procedure to draw. Here I wrote directly. This is the diagram V and IA. IA is in phase with the voltage because this is UPF load and E naught is equal to, we know that IA B plus IARA plus Z IA XL plus Z IA XA. This is so. This is what we need to complete. This is IARA up to here. This is IARA. This is in phase with the IA. Nothing but whatever IA direction is in this direction, IA is in this direction. Definitely IARA drop also will be in the same direction. So next one is IAXL. IAXL. This is IAXL. Why we need to take IAXL is before than armature reaction because after producing the flux, those flux how affecting on the main field flux such a that is called armature reaction. That's why after production of the flux, armature reaction will be takes place. That's why first we need to take leakage reactance and then we need to add IAXA, IAXA in this direction, IAXA in this direction. So if you add all these two, this is total. This is nothing but IA excess, IA excess or justly I excess. So if you add this total, this is nothing but total induced EMF, and this is total impedance. So this is impedance triangle like this. So this is IARA, this is total IA excess. So resistance, sum of the resistance are RA square plus XS square, which is equal to ZS, synchronous impedance. That's why this is a IA ZS. This is the diagram. Next, simply, if you know UPF, unity power factor load, then you can understand lagging power factor and the leading. Simply for the lagging, this IA will be shifted to some angle behind the voltage V, and for the leading load, this IA will be shifted to the in front of the voltage. This is like this is theta, and here also some theta. I think that I will be lags to some angles, will be lead some angle. Based on that one, lagging and leading loads, you can understand very easily. You can see this, that this is a lagging load. So for the lagging load, for all this, for all cases, for all the loads, so this is the equation is mandatory. E naught is equal to V plus IA, or A plus IA, ZIA XL plus ZIA XA. These are common for all lagging, leading, and every load. So look at this one. This is voltage V, and I wrote with some angle. This is with some angle, and next we completed, and the next IARA. IARA is nothing but IARA must be in parallel with the I. So this is I. Parallel to the I is nothing but IARA like this. This is IARA. Next, IAXL must be 90 degrees with the IARA. So here 90 degrees. So this is IAXL, and the next this is completed, and now IAXA. This is IAXA. This total is called as a total XL plus XA is nothing but XS, and this total I is nothing but IA or I directly. So this total is sum of the total from up to here is called IA into ZS. IA into ZS. This is the vector diagram for lagging power factor load. Only the difference is current I lags some angle theta. So the next one is leading load. So this is leading load also similar to the previous one, but so this is voltage V, and current I. I leads some angle theta. So IARA drop is in parallel with the I. This is I. In parallel with the I is nothing but IARA drop. Exactly the 90 degrees IA XL, and the addition to that one IA XA. So this total is called nothing but I XS. And sum of these two is nothing but I into ZS. So the total is E naught induced EMF in the alternator. These are the different types of vector diagrams when alternator is loaded. When alternator is loaded, that is a loaded alternator. Next one is armature reaction. So first of all, what is the armature reaction? So for that, I want to go back to your previous semester DC missions. For example, this is so this is a north pole and this is a south pole, and flux always passes from north to south like this. Let us take a conductor. This is the conductor, and these are the split rings. From this one, some of the battery or resistive load, whatever it may be, that is connected. So now, so if you rotate this alternator, for example, this is A and B side. If you rotate the alternator in the clockwise direction, and EMF induces in this across this conductor, and current passes in this direction, and flux also produces surrounding of this conductor, and these flux. So after cutting, according to the Paradise law of electromagnetic induction, if you rotate this conductor between the north and south pole, then the EMF will be induced in the conductor, and then current passes, and according to the right hand thumb rule, and flux will be established as surrounding of this conductor like this. These flux, these armature flux, these are called armature flux. Those armature flux, how the armature flux are affecting these main flow flux. These actually you can see this direction, these flux, this north and south pole flux are called main uh, field flux or main flux. Main field flux or main flux. So how this armature flux affecting on main field flux? Nothing but whether the armature flux strengthening the main field flux, or whether the armature flux weakening the main field flux. So such an effect is called armature reaction. Armature reaction. Think about how the armature is reacting with respect to the main field flux. How the armature flux is reacting with the main field flux. So such a uh, effect is called armature reaction. This is a basic concept, and the similar concept is exists in the synchronous missions. So that how it will be, I will explain one by one. So, so this is the definition, the effect of armature flux on main field flux. So the armature, so I already discussed the initial stage, and the armature reaction does not affect on power factor in case DC mission, because DC missions is not affected by the inductance and the capacitance effects. That's why it is independent on power factor. But in case of a synchronous mission, it is a AC alternator, nothing but AC generator. AC is nothing but a inductor and capacitor will affected by the AC supply. That's why the power factor come into picture. The power factor come into picture. That's why the armature effect depends on the power factor. Power factor. In case of DC machine, uh, cross magnetization effect and demagnetization effect will appear. But in case of AC alternator, along with that, along with these two, extra one is uh, magnetization effect. Magnetization effect will be takes place. So I will explain in a step-by-step manner. So first one is the UPF load is nothing but a cross magnetization effect. Lagging power factor is nothing but demagnetization effect. So I should not say this is lagging. I should not say this is lagging, and I can say that this is purely lagging power factor. Then only cross magnetization, and a purely leading power factor. Then magnetization. For example, this is voltage and this is current. Here, demagnetization. Why it is purely lagging? Because 90 degrees. If current here, this is a approximately I took this one. Just I want to draw an exact 90 degrees with this so that you can understand better. So here, this is a I exactly 90 degrees leading, so that this is a magnetization effect. Magnetization effect. For example, other than these two cases, the current may be like this voltage, and current will be not exactly with the uh, 90 degrees lagging. This is theta is always less than 90 degrees. That's why in case this is called a cross magnetization effect. And here this is lagging. That's why demagnetization effect. Demagnetization effect. For example, the voltage is like this, and the current will be not exactly purely leading. Current will be like this, and if it is like this, this is a less than 90. Theta is less than 90. That's why this is a first one is cross magnetization effect will be takes place. Second, uh, so this is leading in nature. That's why magnetization effect will be takes place. You may get it out why cross magnetization effect will be takes place. Why cross magnetization effect will be takes place? Because if it is 30 degrees lagging or 40 degrees lagging, definitely resistive nature will affect. Resistive nature, because of this resistive nature, purely resistive nature, UPF load, purely resistive load, nothing but UPF load. Because of this one, cross magnetization effect will be takes place, and this is possible only the theta is less than 90 degrees only. So this X may be inductive load or capacitive load. Based on inductive load, this is demagnetization effect. If it is capacitive load, cross magnetization effect. If the theta is less than 90 degrees, then both either definitely if the theta is less than 90 degrees, compulsory cross magnetization will be takes place. This cross magnetization will be takes place. But that based on load, whether it is either demagnetization or cross magnetization will be takes place. So I will explain in detail how it will be. The first one is UPF load or resistive load, pure. I'm taking pure resistive load. For the pure resistive load, the effect is cross magnetization effect. Cross magnetization effect, which means, so I will explain one by one clearly. What is cross magnetization effect? Cross magnetization effect. What is demagnetization effect? What is a magnetization effect? For example, these are the main field flux. Look at this one. I'm using with a black pen. These are the main field flux common for all cases. I'm writing here, and with red, I'm drawing a. This is a phi m or pi f, and this is a phi a armature flux. Demagnetization flux, nothing but I'm writing exactly opposite. So this flux is nothing but phi a, and this is phi f field flux, and this is nothing but a field flux. Magnetization effect is nothing but the armature flux is like this. Phi phi a will be like this. Nothing but look at this one. Cross magnetization is nothing but just like a crossing each other like this, crossing each other. Demagnetization nothing but opposite to each other. Nothing but phi f minus phi a. Nothing but resultant flux will be decreases. Nothing but field flux will be decreases. Here, field flux and armature flux both are adding, so that this is called magnetization. Here, flux is opposite to each other, so that flux is decreasing, so that demagnetization. Flux is increases in this magnetization effect. That's why this is called magnetization effect. Here, in this direction, flux or main field flux decreases. That's why demagnetization effect. This is very simple. So look at this one, how it will be. So these are the main field flux. You can see that these are the main field flux. And, this is the AC waveform, main field flux. And the next, you can see the this is the armature flux. So look at this one. Armature flux and main field flux differ by approximately 90 degrees. Approximately 90 degrees. So this is approximately both are differ by 90 degrees. That effect is called a cross magnetization effect. So this is the thing with so this is it will be generated like this. After that, armature flux will be generated like this. So this is phi f and this is phi a. So the phase shift between these two is called 90 degrees. Between the two flux, 90 degrees. That's why this effect is called cross magnetation effect. So this is a in a linear manner. If we take this alignment, this is a main field flux direction, and you can see this armature flux. Armature flux, nothing but you can see that, for example, main field flux, after cutting the main field flux, armature flux will be establishes, and the phase difference is nothing but 90 degrees. That's why uh, the lagging in nature. That is the lagging nature. That's why they represented the this is the armature flux and lags at 90 degrees with the main field flux. That's why because simply after cutting the main field flux, armature EMF will be induced in the armature and the flux will be produced in the armature. Nothing but that effect will be after the main field flux. That's why this is a phi A is lagging, and if you represent like this is main field flux like this, and this is a armature flux. This is direction. This is total is nothing but phi A, and this total is nothing but phi F. And this effect is nothing but a cross magnetation effect because of flux are crossing each other. So this is about cross magnetation effect. Next one is a lagging load. Nothing but purely lagging load. So how it will be. Okay, this one, this is north and south pole. This is the main field flux. For the purely lagging load, exactly this main field flux and armature flux should be opposite to each other. That's what I explained in the previous few minutes back. Look at this one. So I already told you that is you can see this main field flux and this is armature flux. Both are exactly opposite in nature. So this is positive side and this is negative side. This is positive side and this is negative side. Both will be cancel each other, cancel each other. So that's why total flux, nothing but a field flux. Field flux will decreases. That's why this is called a demagnetization effect. Total flux are decreasing. So this is, for example, phi F field flux. This is field flux, and this is armature flux. So armature flux are opposite, nothing but negative. That's why, for example, main this is nothing but 30 milliweber, and this is phi A is nothing but 16 milliweber. The resultant will be 14 milliweber. I think that the total flux will be decreasing. That's why this is called demagnetization. So this is 30 milliweber. So magnetize. This is the total flux, and we are demagnetizing. We are demagnetizing this flux. That's why this is called demagnetization. That the demagnetization effect is because of this armature flux. Armature flux. This is a. So I already told you this is I phi F. Phi F is in this direction, and opposite to this one, this is a phi A. Opposite to the main field flux, armature flux will be exist. So you can see that representation. So in the previous section, I forgot to say one thing. Here, this is induced EMF for phase in the same direction. Phi A, IA will be appear. Nothing but phi A will appear. This is nothing but cross magnetation effect. But in the due to the lagging nature or due to the purely inductive load, this flux will be produced in the field flux. Field flux will cut the armature flux, armature winding, and EMF will be induces, and the flux will be established after 90 degrees. And this flux is nothing but the armature flux. And this armature flux is lagging in nature, purely lagging in nature. That's why 90 degrees difference. That's why total will be phase shift will be 180 degrees. So this is phi F and phi A. This is phi A, total 180 degrees phase shift opposite to each other. This is for example, I already told you phi F, this is opposite to this one is phi A. So both are opposite to each other. So this is the representation of purely lagging load connected to the alternator. Then the demagnetization effect will come into picture. And the last one is leading power factor are purely capacitive load. You cannot say that leading capacitor, it is a purely capacitive. So in this case, the main field flux and armature flux both will be adding each other, but both are in phase. So I will explain how it will be, so you can see that very easily. So this is a phi f field flux, and if the field flux cut the armature, and EMF will be induced EMF for phase. And if you connect the leading load is nothing but so for example, this is UPF load, current will be here, and for the lagging load or purely lagging load, current will be behind this one, purely lagging. So current will be here, in the same way flux will be here. This is armature flux. For the purely purely capacitive load, the current will be exactly 90 degrees leading with the induced EMF for phase. That's why this is current here, IA, and the same way flux also will be in phase with the IA. Is nothing but IA will be leads the induced EMF with 90 degrees if we connect the purely capacitive load. That's why you can see this clearly. This is phi F. This is induced EMF for phase, and the flux production also in 90 degrees with the leading, as it is purely capacitive load. That's why these two are in phase. Nothing but phi A is adding with the phi F, the total flux increasing. Flux increasing is nothing but that is called magnetization effect. So you can see that clearly. So this is the adding in nature because of this purely capacitive load. So induced EMF exactly 90 degrees lagging with the main field flux in the armature, and IA will flow in the same direction of main field flux as it is a purely capacitive load. So that the flux also same will be in the direction of main field flux. That's why the total armature flux and field flux adding in nature. So that is adding is nothing but magnetization. These are the three effects because of the armature reaction in the alternator. And so this is I already explained. So I'm giving a conclusion. This is extra thing, nothing but you know very well about the cross magnetization, demagnetization, and this is UPF load, or you can see this. This is UPF load or purely resistive load. ZPF lagging is nothing but pure inductive load. ZPF leading is nothing but pure capacitive load. So we discussed only these three loads: UPF load or uh, resistive load or inductive load. So L load, this is a L load. This is capacitive load. So because of this UPF load, purely cross magnetization, which I already discussed, because of this ZPF lagging, purely demagnetization effect. For ZPF leading, purely magnetization. And this effect is only for generator synchronous generator or alternator or synchronous generator synchronous generator. And the remaining cases are, so look at this one: 0.8 power factor, or 0.6 or 0.5, whatever it may be, 0.1 to 0.9 lagging. Between these, we can say that lagging, that may be 0.8 or 0.6 or 0. Whatever it may be. If in such a case, resistance effect and also XL effect, both will be takes place. Because of this resistance effect, cross magnetization effect. So this is not a purely cross magnetization effect, just a cross magnetization effect. And because of this inductor load, demagnetization effect, not purely cross magnetization effect, just demagnetization effect. So because of this lagging power factor, R and J XL both will be present. That's why partially demagnetization effect and partially cross magnetization, both effect must be appear. And in case of leading load, in case of leading load, and simply r minus jxc, minus jxc, r is nothing but partially cross magnetization effect, sorry, partially cross magnetization effect, and xc is nothing but leading, that's why partially magnetization effect. So these three cases are common, but these two are the extra cases, and this will depends on, for these two common cases, cross magnetization, partially cross magnetization effect will appear. Here also partially cross magnetization will be appear. But in case of lagging, demagnetization effect, partially demagnetization effect. In case of leading, partially magnetization effect will be takes place. This is all for synchronous motor, sorry, synchronous generator or alternator. But this is if we compare in a competitive exams, you may get questions on synchronous motor also. Synchronous motor also. Synchronous motor is opposite to the armature reaction, opposite to the synchronous. You can say this DC generator is opposite to the DC motor. So you know very well about this will generate and it will consume, it will generate, it give the current, it will take consume the current. So like that synchronous generator and synchronous motor are opposite to each other. So except this case everything is opposite except to UPF, purely UPF, everything is different. So purely cross magnetization here, here also purely cross magnetization, only resistive load. Here ZPF load, here demagnetization effect, here magnetization, here magnetization, here demagnetization. So you can see this is opposite. In these two cases here, cross magnetization present, you can see this cross magnetization present, here also cross magnetization present, here also cross magnetization present in both the cases. But here demagnetization is available, here magnetization available, magnetization effect will available. Here magnetization effect is available, here demagnetization effect will available. These are the differences between synchronous generator and synchronous motor of armature reaction. Just small difference is there, opposite to each other, only for UPF load this is common to each other, but in case of remaining all the cases opposite to each other. So this is all about the armature reaction.